Okay, so welcome to the TCS seminar at Jagiellonian University. Today we have Andrzej Ruciński from Mickiewicz University in Poznań. Please come to the audience. So Andrzej is well known for his research on in extremal graph and hypergraph theory, and today he will tell us about homogeneous substructures in ordered hypergraph matrix. So
thank you. I would like to thank both Bartek and Piotr for inviting me here. It's a great pleasure to be again at the Jagiellonian University. I was here maybe last time speaking, I think it was back in 2004 or something, or 8, long ago. I want to thank you for coming. And today I would like to share with you my recent results obtained jointly with Andrzej Dudek from Kalamazoo and Jarek Grytczuk from Warsaw Polytechnic. And maybe if I get to the last part, then there will be also some yet another co-author I will mention than his name. And it all starts with this core result, the seminal result of Erdős and Szekeres. Here, okay. From 1935, which probably all of you know. I formulated here in terms of permutation rather than sequences, that if you have a permutation large enough, there are two parameters, A1 and A2, and plus 1, then you either got an increasing subsequence of length A1 plus 1 or decreasing of length A2 plus 1. And this threshold, let's call it this A1 times A2 plus 1, is optimal. There's an easy construction I'm going to skip. Now, we got interested in objects which, in a certain sense, could be viewed as very dull, because our object of interest are matchings. Matchings might be very interesting objects if they are within a graph, but a matching for itself is just a bunch of disjoint edges. That's what actually mean. No isolated vertices, just a bunch of disjoint edges. So there's nothing to say about it. But if you impose order on the vertices, the things then become interesting, and this is what we do. These slides are in Polish, but they will change. At some point there'll be a miracle change, and they become English, and then I start speaking Polish, right, to keep the balance. So we have so consider the symbol Mn or Mn2. If we then go to generalizations, denotes a matching of size n. So n is always here the number of edges, and so it's just a set of n disjoint edges. But the vertex set should be linearly ordered, and we'll be working with just typically with a set of initial integers, because it doesn't matter what is the nature of the vertices; they need to be linearly ordered. And then if you have this extra structure of this ordering, then if you look at two edges, they may appear in three possible relations or patterns. Right? These are the three. I'll denote them by R1, R2, R3, but often maybe we'll be referring to them as lines, stacks, and waves. And there is this handy letter notation. Actually, for some reason, it's called Gauss letter notation, because Gauss uses that notation to describe self-intersecting curves. If you think about it, the number of times, anyway, that's the origin of this, but of course this is not relevant to my presentation. So just remember these three possibilities. And okay, doesn't work, but I can use this. Okay, so this is my second slide. Here it's a crucial notion, the notion of a clique, Rj, so there's some pattern and then the clique in that pattern. In that case, so Rj, J is 1, 2, 3, but soon we will be generalizing this notion. So it's important to understand this notion. So it's just a set of edges of our matching subset or set on its own, so that every two of these edges forms the very same pattern, say R1. And here on the bottom, you see examples of such cliques of size 4. So here are there's a line of size 4, and you see every two edges are the same relation. Here is a stack of size 4, and every two edges are the same relation, and so on. And a crucial piece of notation, Z sub J of M, or generally Z sub some pattern P of M, is the size of the largest such clique in a matching. Okay. Why it doesn't work? Should work, maybe. Okay. Have a look, and I'll just use this. Okay, so I hope you see similarity between this structure and these permutations I started with. Thank you. Why in permutations we have these two options? Either you have an increasing subsequence or decreasing subsequence. Just because if you take two numbers for the permutation, either one of the first one is bigger than the other, or the other way around. Two options, two relations. Here we have three relations, so we aimed at a result which would incorporate those three relations and be very analogous to Erdős-Szekeres. And indeed, such a result was actually easy to prove. Too easy, we got suspicious, it's too easy. But I hope you understand what it means. Right? You have a big enough matching, ordered matching on a set of 2n vertices, and the number of edges n is at least this product plus 1, then you must find a homogeneous clique of size bj plus 1, this parameter plus 1, like in Erdős-Szekeres. And there are three easy proofs. I will not go over these proofs in detail. Maybe if you want to see more details about this, and we are suspicious, and indeed, when I was giving a talk about this result 2 years ago in Sydney, there was this first guy, Tony Hume, and he said, oh, but by the way, in our paper from 2017, there's this lemma 25, and we actually prove it, except that they only prove it for B1, B2, B3 equal, so symmetric case. But of course, the same proof went, and they use Dilworth's theorem. So, in fact, this is not a new result, right? We got it independently. These proofs are either using Erdős-Szekeres, or if not, they mimic Erdős-Szekeres proof, and then it follows. So, you think it will work now? Okay. So I will skip this. I'll skip this. Let's just focus on the very last part here. One of the several proofs, yes, but of course, Dilworth came later. Of course, Erdős-Szekeres. Of course, it's all easy, and this optimality is also easy. But I will mention this because later on, for these hypergraph structures, we will use a similar tool, which we could call the kind of a blow up or superimposition of matchings one into another. So it's kind of a blow up. So what that means that the result is optimal. So we should find an example of a matching of size B1 times B2 times B3 without the plus 1, and then show that it doesn't have a line bigger than B1 or a stack bigger than B2 or a wave bigger than B3. And indeed, if you just do this, so let's start maybe from the middle. You take a stack of size B2. Size is the number of edges, right? So that's why it's only 2 here. Right? You have B2 of these edges, and they form a stack. And then you insert inside each of these edges a copy of a wave of size B3. So you have to imagine here a copy of this here and here, same copy. So at this point you have B2 times B3 edges, and there are no larger stack than B3, and there is no larger stack than B2, and no larger wave than B3. That's maybe it's proof, but it's kind of self-explanatory. And in the end, we take B1 copies of this object and put them next to each other on the line. And this final product is what we wanted. It's a matching of size B1 times B2 times B3, and doesn't have anything bigger than Bi. So the largest Rj clique is of size Bj, not +1. So that proves optimality. But this is just a warm-up. Once we are done with this and kind of disappointed that it's so easy and someone else did it also, we said, let's do something more general. So let's move on to hypergraphs, hypermatchings. One disadvantage of hypermatching is that it's hard to draw. And this shocks, right? This is a very simple object. Is a matching, is a 3 matchings of, okay, this is a mistake. That should be M3, M3, because there are just 3 edges. And this subscript N represents, so I just fooled myself. It is not the number of vertices, but the number of this 9 over there on the very top should be 3. Okay, but you can count, right? So there are 9 vertices, 3 edges, each of size 3 is a matching, and they just kind of intertwine like this. So again, this letter notation comes handy. We'll be more and more switching to letter notation rather than drawings, because drawings are ugly, and letter notation is still kind of nice. So it's AABC, ACB, represents this matching. Here is the total number of these objects. I hope you know basic combinatorics. So it's just the total number of ways to partition Rn into sets of size R, and the order doesn't matter. So we divide by n factorial. In particular, what is important to us is that if you take just you take 2 instead of n, so just 2 edges, then we are counting the number of these patterns. How many different patterns can be created by 2 edges? That's what of great interest to us. Like in the graph case, we had 3. In fact, if you plug R equal to 2, you get 3. But if you plug R equal to 3, the next step, you get 10. And here they are. Actually, could you memorize it? Because I will refer very often to all this. There are 10 of them. And the notation is kind of, I put aside this P0, it's a special guy, a kind of a bastard, a bad character. And there are 9 nice guys, and especially amongst them, there are the 4 nicest guys. Because these 4 matchings correspond to, they are all tripartite. Those who are familiar with the interval chromatic index, chromatic number, they know what I mean. Is the chromatic one way to define a tripartite matching or tripartite graph, ordered graph in general is its interval chromatic number is 3, and it's just the notion. You just color as an ordinary chromatic number that you need every edge, no edge to be monochromatic, but in addition, the colors must form blocks of in this order of vertices. You need to start with vertices colored number 1, then number 2, number 3, like that, and so on. So these are the three partite out of these 10 patterns of size 3. So you understand this picture of this table, let's say. There are 10 ways 2 edges of size 3 on an order set may form. And amongst them, so I explain this. There are 9 good ones, and they why are they good ones? Because actually we call them collective, or I'll just be calling them good. A collective means that in fact you can create out of them. You can create out of them all these cliques of any size. Like if you want to, like I was saying before, here you see, back in the graph case, you could create an R1 clique of any length. Just keep adding the edges. You could create any size, any size. And similarly for most of these three patterns, you can create PI. Now we are by PI clique. So PI clique is once again a set of edges. So every two forms the same pattern PI, and you can create them arbitrarily large for all of them except for P0. I will explain in a moment why P0 is so bad. So just remember that there is one bad guy, there are 9 good guys, and among them are these 4 tripartite. And again, I denote by ZP of M the size of the largest P clique in matching M. Here is actually an explanation, a brief explanation why. So, for example, P4 is a good pattern because you can create. And P4 was this one, AB, BB, AA, and you can create any number. You can keep adding E. Yeah, and you can do it with every other one except P0. Because look, if you have P0 and say if A and B, P0 is A, B, B. If you have a pattern P0 between A and B, and is the same matching between B and C, it forces that all the A's are in front of all the C's. So it's a bad thing. You can't even have a triangle. And it was easy, but we managed to characterize all these collectible in terms of block partitions. So you can recognize a collectible pattern if you look at its letter notation, and you can split it into blocks of even lengths. And moreover, within each block, you have the first half and the second half, and they have to be homogeneous. So either all A's or all B's, 50-50 in each block. So here is just one block of length 6, and you have 3 A's and 3 B's. Here you have first a block of size 4, and this splits into A's and B's, and the second one is of length 2, and you have B and A, so again, 50-50. In the middle, they change. You understand this vision? There's one thing, you cannot switch the beginning because the order doesn't matter, so A is always the first letter here. Therefore, for example, okay, there is some combinatorics to that. Using this structure, we can count them. So the total number of these collected are 3 to the r minus 1.
The only way that when the split doesn't exist, it must be when the number of A's is always bigger than the number of B's, and you read it from left to right. I'm not sure about this characterization, but maybe anyway. So, but then it would be some kind of Catalan number, but it isn't. It's this number. So the total number of patterns is this number: 1/2 2r over r. Collectible are 3 to the r minus 1. So the non-collectibles, these bad guys, this number is growing, right? At some point, the majority of patterns are bad. For r equal to 2, all of them were good. There were no bad. For 3, you see, 9 good, 10 total, so just 1. But if you take 4, the number of bad guys is 8 out of 35. And there are 27 good ones. And then also it's good to know the number of R-partite patterns, and it's easy because in every of these, they are characterized by these that these blocks are of length 2, and you can swap A and B, but everywhere except the first one. So that's r minus 1. Okay, and knowing all of this, maybe you can now comprehend the result we got in a paper just published online, but it will be next year officially. So with Dudek and Grytczuk, we got this result that for every R, if you enumerate or just list those
all collectible patterns. There are 3 to the r minus 1 of them, and assign to each of them, like in Erdős-Szekeres, like in our first theorem, a parameter, b1, b2, b3, r minus 1. Then there is a constant, which I don't want to go. We kind of optimize that constant, but it's still not, it doesn't match the lower bound anyway. So there is, so if n is big enough, so it's at least some constant times the product. If not for this constant, it would be absolutely analogous to Erdős-Szekeres, right? You have a product of parameters, and you have more, just plus 1, except that this constant may not be even integer, so I prefer to use it. Then every matching of size n, every R matching of size n, so we are in R uniformity world, right? We have for every such matching, there is a pattern. This plus 1 should be up. Sorry, another typo. That you have a big clique of this pattern. And we got a second part. If you just restrict yourself to R-part-type matchings, but this is really a much easier object. If you have an R-part-type matching, say 3-partite, then every edge goes like this. So this is one edge, here is another edge, and so on. So every edge, in fact, is determined by 2 permutations. The first points go as ordered, and then the second points are for the permutation, and the third is also permutation. So in fact, this theorem could also be easily obtained from many-dimensional Erdős-Szekeres. But anyway, so once again, the second part is talking only about R-partite. So that's why you only have 2 to the r minus y. Otherwise, it's very similar, and there is no additional constant. So this result is optimal, and the construction showing optimality is very similar to what I just showed you with the stacks and waves, putting one inside another. But again, this is restricted to R-partite matchings. And this one is, so this is optimal. However, that was the problem we had, that our result was far from optimality.
Can you go back the slide?
Okay.
In Erdős-Szekeres, you have a strict inequality in statement, what is it, B?
Sorry.
Okay. No. Now you can take back.
Back, okay.
Yeah, it works. Because you push both buttons. This is left, so push it on this side, not in the middle, because they are both pushed in.
Okay.
Now forward.
You want to see what?
Now go back to, you're already behind. Now forward. So the right one. Oh, here. Yeah. So
okay.
That was my question now. Yeah, in the Erdős-Szekeres, this inequality in the middle line is in the B statement, statement B, not A, B. In the middle, it's the one line lower. Here, it's strict, right?
It's
So
it's plus 1.
Plus 1 should be.
Yeah, that's what I said. I think.
Oh, you said
okay,
it.
Yeah.
Okay.
That was my mistake, of course. Sorry for that. So it's not optimal, and we got some tips what's going on, but we are maybe impatient or kind of tired of the problem, and we decided not to pursue it much further, and we published this non-optimal result. Here is, but we observed that there were pairs of patterns which didn't like each other. For example, P3 and P7. Normally, in this blow-up operation, they should always fit together nicely. That one comes inside the other, and you can have cliques of just two types with plenty of them. Here, however, if consider the following object: P3, P7 clique. They are listed there. So consider a matching where every pair of edges is either in relation P3 or P7. Then it's easy to see, very simple argument, trivial, that it has to be pure P3 or pure P7. So there was something going on between these. And P3 and P7, they are like this. So AA, BB, AB, and BC, BB, CC. And it has something to do, actually, a lot to do with the way they partition the number, the total number, which is 2R. Or in fact, because everything is doubled, just as go to R. So this one represents a partition into 2 plus 1, because the first block has 2 A's and 2 B's. The second block has 1 A and 1 B. Here, the first block has 1 and 1, and the second one has 2 and 2. So they are kind of not compatible partitions. And that was what was causing this. And then as soon as we posted our paper on arXiv, Lisa Sauermann and Dmitry or Zakharov, they started working on it, and maybe after 8 months or so, they sent us a manuscript, which will be published soon, I guess, where they improved our result a lot. Almost optimal results they obtained, and I'm going now to briefly describe it. So their tool was actually these partitions. So once again, if you have a pattern which is collectible, so it's split into blocks. Every block has these 2 halves, 2 homogeneous halves. So it has size, say, even. So it's 2 lambda 1, 2 lambda 2, and these lambdas, they partition number R, because the whole thing is 2R. So they partition number R. So once again, to every pattern, we can assign a partition of R, which I denote by lambda of P. And so here are examples, like back to the case R equal to 3, it's just this trivial partition, just 3, then 2 plus 1, 1 plus 2, and then there is this 1 plus 1 plus 1. That's all you can get for R equal to 3. And let's define a refinement, a relation, which is a refinement of these partitions in the usual way. You know how to refine a partition of numbers, but the terms are ordered. So the refinement must be obtained by splitting one or more of these summands into finer numbers, so into some sums. For example, lambda 3 which is this partition, is coarser, or the other one, lambda 2 1 is a refinement of lambda 3, because 3 splits into 2 plus 1. And for example, 2 plus 1 is bigger than lambda 1 because you can obtain by splitting 2. You can't switch orders, anything, just that's a very kind of natural and easy, I believe, to comprehend relation. We still have some piece of notation. If you fix such a partition, you consider by P of, is a calligraphic P, is a set of all partitions, or all patterns with this partition. So for example, P of lambda 3 is just P1, P of lambda 2 1 is P2 and P3, and so on and so forth. P of lambda 1 1 1 are these all 4 3-partite, because they all have the same. And here is the first part of the result. Maybe I now do it so that you see both parts. Is it possible? No. Because this is the full. Okay, one at a time. So this theorem of Sauermann and Zakharov says something similar to all these theorems, but the main difference is that in Erdős-Szekeres, in our theorem, here we just had the product of these parameters, and they have a sum of products, and they sum over all chains in this partial order of length R. So they always begin with the most coarse partition, just R, and they end in this bottom partition, the finest partition, 1 1 1 1 1 R times. And
it's a maximal chain, yeah? It's from 1 1 1.
They are maximal, of course, because you have one maximum element and one minimum element. And so for R equal to 3, there are just 2. two such chains. For larger R, actually you can calculate how many such chains are there. It's just R minus 1 factorial of these summands. And then for each such summand, you take all patterns which belong to these families P, so which do have these partitions, and take the product of this BP, and plus 1, of course, at the end. And then the same conclusion, then for every matching, there will be a partition which has a big clique in it, bigger than BP plus 1.
So it's a stronger statement because in your type of theorem or in Erdős-Szekeres, you take them all together, and here it's like a finer.
Yeah, it's a finer. They use this observation we did that some patterns do not go well together, and that was the reason that they are not comparable with this relation, so they have to be on separate chains. And here is the moreover part. If you still remember the first part of the theorem, the difference is that here you don't have any sum, but you have the maximum over all these terms of that sum. So it's not if you still if you look at this, is the sum of such objects, of such products. Here you have maximum, and of course without plus 1. Then there exists such a matching, so that it has this size. So it doesn't match that other size. They don't differ by 1. They differ by some constant. But the constant depends, in fact, multiplicative constant, but it only depends on R. So in that sense, their result is almost optimum. Here's an example for R equal to 3, so that you can put your hands on it. The first part, the positive part, says if n is at least 4 times, and as I said, there are just 2 chains, so there are 2 summands in that summation, and I factor out the common part. The common part is this coarse partition, lambda 1, and this lambda 3, and this finest partition, lambda 1, 1, 1. So these are the 4. These numbers correspond to the 4 R partype. And here are the 2 options. Either in the chain you take P2 and P3, or you take P3 and P7, because either you take 2, 1 or 1, 2, but you can take both because they are not comparable. And then in the second part, you just take this maximum. Okay, so there's still something to be done because they are still away by, but the constant is only in terms of R. But if you are interested in some extremal consequences.
Do you believe that the upper bound is tight?
Sorry?
Do you believe that the first part is tight? The lower bound just gives you construction for each chain, yeah? For each chain is tight.
I'm not sure about it. I would need to really understand the proof of the first part, what they did. It was more complicated. I will not show you this. But Sauermann and Zakharov, they didn't even say. They only observed that if R goes to infinity, they go to, they kind of, it's a special case. So let me say what the special case is, the symmetric case. But we need one more observation. If I take one such chain, such maximal chain, and count how many patterns are in this union. So you see, the first one is just 1, then 2. It's easy to calculate. It's just 2 to the R minus 1. So if you take all the BP equal to B, so all these products are just B to a power, it's the same power, B to the power 2 to the R minus 1, because there are exactly that many factors in each product. So once again, that was the sum of products, and in each product, you have the same number of terms, factors. Because the number of products here is 2 to the R minus 1.
Oh, okay.
The number of these BPs here is exactly 2 to the R minus 1 for every chain. Which, if you plug in, you got this inequality, and now you can redefine it in terms of. We just want to define an extremal parameter. So L of M is just the largest clique whatsoever you can find in a matching, no matter which P. So it's the maximum over P of the ZP of n. Understand this? You just go for the largest. Doesn't matter which P. And then we take the worst case, the minimum, over all matchings of size n is given R. And then this parameter, it follows from this. If you just solve it for B, it's basically, if you swallow the constant, it's just n to 1 over 2R, 2 to the R minus 1. So, in fact, for R equal to 2, for example, the initial case, the graph case I started with, it says that in every matching of size n, you will find one of the three things at least of size n to 1/3. For R equal to 3, you will find one of the 9 things, 9, which is as big as n to 1 over 7. See, our result, which we gave this not optimal result we got, would only yield 1 over 9 here, because we treated all 9 patterns equal as brothers, and unfortunately there are some enemies.
And here the lower bound is matching because this constant is in R.
They only differ by a constant in R, so, and we swallow it here, so it's the same. And as I see it, it's an analogy, because if you take the symmetric case of Erdős-Szekeres for permutations, you know that there will be a monotone subsequence of length square root of n. You don't know which way monotone, but okay. And here, and yeah, I'm not sure if I have time for that. I still have some time. Okay. So here is my attempt to explain the second part, the construction. The construction, how to get this part. So how to construct, given B1, BP for every P, how to construct a matching of size, just product of these, so that you don't have any P clique bigger than BP. That's what we want to do now. And for this, and actually this notion of this blow up was given in our paper, but we didn't follow it to the full strength. So say we have 2 matchings, M and N, 2 R matchings, and just denote by T the size of the second matching. We need it. And then we define the blow up, the N blow up of M, which is denoted by M brackets N, as follows. You take this matching M, it's a natural blow up. Every vertex is replaced by a set of size T. So U sub I, vertex I becomes U sub I. And then for every edge of M, which has R vertices, you look at these R sets and put on these R sets together a copy of this other, of the matching N. Matching N has T edges, so it fits exactly, because it has size T times R. Is it clear? Here's an example. The important thing is that if you count, trivially, right, the size of the blow up is just the product of the 2 sizes, right? Because every edge becomes n copies. There are n edges. From every edge of M, you got n size n T copies, T edges. So here's an example that MB and BZ. Here I chose an easy example that N is 3-partite. See, there are 3 edges, X, Y, and Z. Once again, I identify edges with the letters, right? So X means an edge, EX, something.
So again, every edge of N you replace by a copy of N. That's the way.
Yes, but I need to make room more. So I replace every vertex by a set of size T. And then, so altogether, I have a set of size R times T, exactly as the number of vertices in N. And I just put it in the right order, of course. Everything is in order. Here's an example. I don't know if you can have time to really follow it, but you see, here was this M, and there was 3 occurrences of A, because the edge A has 3 vertices, 1st, 3rd, and 7th. And on 1st, 3rd, and 7th position, now I have not a single vertex, but a set of vertices what size? 3, because n has size 3. And if you look at these three sets of size 3, here I insert a copy of n. But instead of using XYZ, I'm using new letters because I want to have new edges every time. So this DEF, EFD, and FD is a copy of n. And there are 3 other copies of n. But the main thing is here that we have two kinds of edges in this result, in this blow up, or pairs of edges rather, pairs of edges. One called n pairs and then m pairs. N pairs are like D and E, so they come from the same copy of n. And then the m pairs, well, they come from different copies of n, like this. And there's a bunch of observations. One is trivial, although maybe, I don't know if you can see it the first time, that for every n pair, like this one, DE, if you look at the patterns they now form in this blow-up, it's the same pattern as they originally formed. So like DE are the same as XY. And let's call it n inheritance, which you get for free. But what we're really after is a similar property with respect to m. So we call m an m inheritable if I take two edges of m and then 2 edges from the corresponding copies of n, they also should have. I invented this notation as I went writing these slides. P of GH is the pattern they form. 2 edges G and H form. Now I'm switching to a different notation, but it's clear what I mean, that they should have the same pattern. For example, DG has the same pattern as AB. And then the observation is that if you have this M inheritance and this free N inheritance, so both you have, and the sets of patterns which appear in M and in N are disjoint, then if you do this blow up, the largest peak clique has the same size as the largest peak clique in either M or N, depending where does this peak come from M or N. In my example, unfortunately, this is not the case because these two sets, the patterns in M and patterns in N they have something in common, and you can easily see that there will be a P5 clique in the blow-up, which is bigger, 3 than what it was 2, but it's not maybe so important. The important thing is here. No, actually, this is maybe the most important, that the number of, the sizes of cliques don't grow. So you can make this blow-up, you can superimpose the blow-up over and over, as long as you have new patterns. You will not increase any previous cliques over any previous pattern. And by the end of the day, maybe you will have all of them, and you got a counterexample. And there are these observations. The first 2 lines we did. We observed, first of all, that if n is R-partite, this second guy, n, is R-partite, then M of n, the blow-up, is always M inheritable, no matter what M is. It needs some second of thought, but because they fit nicely. On the other hand, if M, this first guy, is a line, so it's like all A's and then all B's and nothing else, then it's trivially also M inheritable because this M of n is just disjoint copies of n lined up. So you see, n R-partite or M line, they force this precious property. But what Sauermann and Zakharov observed, actually a referee observed, but probably there was one of them or someone who, anyway. So they observed that it is also true this this M inherence follows if you have this property that all patterns if you take every pattern in M and every pattern in Q, the patterns in Q are refinements of the patterns in P. So if you look at these 2 lines, it means, in fact, if you have the R-partite, it is a finest partition, so it refines everything. So that was like a special case, and this was also a special case, because if M is a line, is a coarse partition, just in one, R equal to R.
I don't get.
Okay.
But is it a statement that, in fact, for every P in N, for every Q in N?
This is just the sufficient condition for the same conclusion, which I didn't write here, that M is inheritable. So it's broader, it contains the other. We stopped here, we got some partial results. They went all the way, because we didn't even work with these partitions, and they did. And here is just, again, R equal to 3. What you can do with all of this? You can take, you can iterate blowups. Look how we start. We start with the 4, in any order, 4 3-partite matchings. They all have this finest partition 1, 1, 1. So if you go say K9, K8, K6, K5, if you stopped here, K5 up to K9, so you have like three steps of this operation of blow up. Then you got a matching of size A5 times A. Oh, I need to one more piece of notation. Ki is just a pi clique of size AI, because that's what we want. We want to show that there are no bigger cliques than AI. So Ki is a clique of size pi clique of size AI. If I take such a clique and take the blow up, so K9 blow up of K8, I got a clique, not a clique, a matching of size A8 times A9, and every P8 clique is at most A8, and every P9 clique is at most A9. And I keep going. I take now K6, and again, it will be, if I take this blow up, I will get now a product. So the size of this matching is A6 times A8 times A9, and every clique is of the right.
Is there some reason that you avoided 4 and 7, or just?
This numbering had some reason in our paper, which it doesn't have here. But I got so used. No, but he's asking why 5, 7. This was just absolutely for you. It's absolutely random, not random.
Just one chain.
This corresponds to one of the chains. Yes, there are 2 chains, and this is just one of them. This is just an example. So, and we keep going. Now look, then comes K3 and K2. K2 and
it covers both statements that you have about, right? Okay.
We are proving this second, right? This construction. Yes. So once we are done with the 3 partites, then we take K2 and K3. They have both partition 2 plus 1. So they satisfy the property. If you take, say, K3, then, so this K5, K6, K8, K9 blow up is our N, and K3 is our M. So again, this property satisfies that for every 2, you have this refinement. So again and again, and in the end, you have K1. So this matching has this size, A1 times A2, and so on. And for every I, the largest pi clique, every I from the set, 1, 2, 3, 5, it has size AI. That's how they construct it. Okay, how much time I have for this last part? Still a bit. Okay, so once we are done with this, we thought, how about almost all or typical matchings? So you just take one at random. In this nice introduction, Bartek says that I am expert in extremal theory, but I used to be an expert in random graphs, and I like random structures. Also, probably you understand by extremal also random. But anyway, so it's one of the things I also like, and also Andrzej Dudek. So we went after this situation. So you take now one out of all, and remember, all was this formula which I denoted for short by lam alpha n r. This is the total number of such matchings, and we take one with uniform probability, and we denoted by rm, so random matching. And fair still is the old paper, not old, but the one before, which will be published, always published. We proved if you take any collectible pattern, then asymptotically, almost surely, the largest p matching, p clique is in a random matching, You take any of these collectible patterns. Then the largest clique has size n to 1 over r. And there is this analogy also back with the permutations, because for random permutations, there are results even much sharper when the constant is also determined asymptotically, that you know that with high probability, a random permutation contains an increasing subsequence of length square root of n, or a decreasing sequence, it's n. So that's the main difference between the results about random structures and results, extrema results before. Before we only concluded, like in Erdős-Szekeres, that there is maybe one pattern which is plenty, but we can't say that two or all of them are plenty, because of course, trivially you can show otherwise. But for random structures, like for random permutations, you have both, or you have all big. That's the difference, right? And all these results we got about random matches are of this kind, that we can prove it for every pattern. Here is some idea of proof. Upper bound was very easy. We use the first moment method by this means. So we denoted by x sub k the number of p cliques of size k. And then we just estimated the expectation. How to calculate the expectation? You have to choose place for that p clique to be. So you need to choose r times k vertices, because once again, k edges means r k vertices we need. So choose them. Then there's just one way to plant such a clique on a given set of vertices. Then you extend it in an arbitrary way and divide by total number. And if you do the right calculations, you can upper bound it by this exponential, which clearly goes to 0 if k is bigger than some large enough constant times n to 1 over r. Right? That's really an exercise. And for the lower bound, it took a little bit longer. We had to define this notion that an edge spans a bunch of disjoint edges, disjoint sets. You have to have r disjoint sets, and then you take this random matching and ask. Okay, you have a matching now, not yet random. You have a matching, and you have these r sets, and if this edge takes exactly one vertex from each, we like it. We call it it spans. This edge spans these sets, or the edge spans the edge. The set spans the edge, whatever. Is it clear? Okay. And now comes the crucial lemma, which says that if you have r such sets, say each of size t, then if you take a random matching now, the probability that no edge spans these r sets is very small, or is bounded exponentially by it. Crucially here is t to the r and n to the r minus 1, and some constant. So this lemma is very nice, and it's not very difficult.
What is t?
C is this number, 1 over 2r to the r. T is just a parameter. T is is the size of all these sets.
Oh.
All these sets have the same size t. And in application, when we actually want to prove this lower bound in our theorem, we take t equal n to 1 minus 1 over r, so that if you take, then k is defined by n over t, which is exactly what we want, n to 1 over r. Let's assume they're all integers, just not to worry about. So we partition the whole set of vertices into rk sets of size, each of size t. So they actually cover, they make a partition, because r times k times t is r times n. It's the whole vertex set. And then we take like a template p clique on k vertices, and then associate one-to-one the vertices of that clique with these sets, and then define a random variable for each edge of this template. If in the random matching there is an edge which spans exactly these sets bj which correspond to this edge. Maybe I draw a picture. Here is yeah, maybe like this. Here is a copy of P9 clique. Sorry, yeah, P9, P clique size 3. So I have 3 edges. If P9 was just AB, AB, AB. So I take one edge is 1, 4, and 7. Then I have another edge, 2, 5, and 8. Sorry, but I warn you, the drawing is not nice here for hypergraphs, even hypermatching. So anyway, this is our template K. This is just 9 vertices, and here is the set of 3n, because R is 3. So we have this set of all vertices in our big, and now we draw a, but we partition it into same number. Here was 9 vertices. We have these sets B1, B2, and so on, B4, B7, and so on, all of them. But I just want to focus. And now I like it if this random matching produces an edge which spans these 3 sets. I like it because I can count it as 1 toward my. I want to show that there will be a large P9 clique. Coming back to this notation, if all the II were 1, we would get then in our random matching a P clique of size K. But of course, some of them can be 0, so we actually get an X. We got a P clique of size X. So all we want to do is just to then estimate X, the random variable. How many times we are so lucky that we get an edge spanning these 3 sets or R sets, which corresponds to an edge. And the expectation is easy because, of course, it's a sum, and then because X is a sum, and then for each one of those, we use the lemma, the negative form, so it's 1 minus. And if you now substitute for T what we got here, and this is N to R, we got, they cancel out. They cancel out. This T and N cancel out. So we got a constant. So the expectation is of the order of K. That's what we like. The last step is to get concentration, and we use Talagrand inequality for permutations. Why for permutations? Because we can practically generate a random matching by taking a random permutation of length Rn and then chop off consecutive blocks of size R. These are our edges. Of course, we got because order doesn't matter here, and then also you can swap the order. So it is equivalent. It's not 1-to-1, but you can use permutations to generate matchings. And that's why we can use Talagrand inequality. I will of course not go into details, but it's kind of a standard approach. And so now just maybe briefly let me tell you what else we did. So this is now a new paper where a new guy is on board. This is Jakub Przybyło, this P from AGH, whatever, from Krakow. And so what we got interested in now, instead of talking about a single pattern, we take a bunch of patterns and define this P clique by taking the whole set of cliques. So, for example, the first result we got, which is kind of complete, we take 2 patterns and we want to see how large is a sub-matching in the random matching, so that every two edges either form P or Q, nothing else. And there are cases because if what happens is that the largest you can get is when these two patterns are not only good, but also compatible. And compatible means, again, same partition. So, for example, P2 and P3 are compatible because they have same partition by numbers, right? It's 2 plus 1, 2 plus 1. Same P4 and P7. All these four are compatible, every pair, because they have the same partition. So for such guys, if they are compatible, we got a higher threshold, n2 1 over r minus 1. If none of them is collectible, they are both bad, we can only get a constant. And for all other pairs, we got the same threshold as for singletons. And the previous theorem, n2 1 over r. So but anyway, it's a nice full characterization. And we got also results for example, if you take all r-partite to one basket and one, then we are after a largest r-partite submatching in a random matching. And it turns out this is linear in n with this asymptotic formula. For r equal to 2 is n over 2, and this solves Bosek's problem with socks, which I don't have time to say, but you can ask him what was his problem with socks. It was like pairing socks and putting into a drawer, and how many you still.
What's the problem?
Then there was one more result when we take, here is work in progress, and we are not yet fully satisfied because we can only make some touches. We have some cases, but the whole thing is still open. For example, we can take one less. So all r-partite but one. So this 2 to the r minus 1 minus 1. For example, for r equal to 3, we had 4 tripartite. Let's take three out of them, not 4, and see how big clique you can get when you can only see those 3, but not the 4th guy. And it turns out that the threshold gets lower, right? It's 1 compared with this. Here was n, here's n1, n2, 1 minus 1 over r. And there is one more result, but I'm afraid I will not have time to explain, where we have some situations where our set of patterns form kind of, they are obtained from each other by swapping A and B's within certain blocks. For example, you have P here, and you can obtain Q if you swap the last two segments, AABB and BA. You can either leave it as it is or swap. There are two options. Here, because we have two such groups of blocks, you never swap the first one because it has to begin with A. But the others you can independently swap. So, for example, in this case, too, out of this you get 3 things because you can swap one of them at a time or both. And so it's kind of nice structure. And for this structure, simply we can use the same technique of proof. So we kind of stretch how far we can use our proof technique, and we also can do it for such. We call them full houses. Full house means that you can take all these possibilities. But as I said, this is work in progress, and there are still many open problems here. We would like to have eventually a result saying that for every subset of patterns, we would like to estimate the largest clique, the size of the largest clique. Thank you.